experiment on wave and group velocity and the superposition of waves. It uses two audio oscillators that can be set at the same or different frequencies and a dual trace scope. The output for this audio oscillator comes in on the B channel, which I can pick up here, and I can raise the intensity. The output from this audio oscillator comes in on the A channel, and the only difference between them is that one is synchronized and the other isn't. The A channel drives, the B channel in this case drives the synchronization, and the A channel is free, and so that if I change the frequency a little bit, it'll change the time at which it comes in and give it a velocity. So that this one is standing still, it has zero velocity. This one has a slightly different, has a velocity which I can adjust from zero either forward or backwards. Then I can look at the two waves put together. In this case, they have different wavelengths. I can measure the wavelength of the A one by saying they're 1, 2, 3, and so forth in a screen width. I can measure the B one. Well, it moves. How can I measure it? I can take the synchronization wire momentarily off the B channel, put it on the A, then it'll stand still while I measure its wavelength. Having measured both wavelengths and measuring this velocity in screen divisions per second, I can show them together. They're different wavelengths. Sometimes they coincide, and at other places they cancel. So now I will get groups which travel across, and I can measure the group velocity for a given wave velocity and the group wavelength, and see how this checks with the calculations. I can start with a variety of frequencies. This is now around 5,000 vibrations a second. The experiment's a little easier to do with lower frequency, 2,500, but we had trouble with an interference between the frequencies of the television sweep and the frequencies of the scope sweep, so we picked one in which the flicker was a minimum. You can still see some of that interference on the pattern here. Now they're both at about the same frequency. If I get them more nearly exactly the same frequency, that should stand still. And I can see now that they either match or don't match. I can raise that. Now they match, now they don't match. Let's let it go a little slower. What to do this high frequency. Get them almost the same. It's about as good as I can do at this high frequency. Now they don't match, now they match. If I switch over to the added position when they match, I get a big thing. If I switch over to the added position when they don't match, I get a small one. Now I see the phenomena of beats. And in fact, the beats are really groups because there is a difference in wavelength. If the group is very long, to see it, I have to go to a very low time scale. And as that sweeps across, you can see that there are really groups coming at me here. Now I'll go back to show this just on this B channel. Notice it's going across, and I can change it. Suppose I want to go to a shorter wavelength. I raise this, and I find that there are a number of places where it doesn't make sense at all. But as I raise it, finally it comes to another one where I get a single wave. And that now has a shorter wavelength. If I show that on top of the other, well, that's the same, pardon me. If I go to a higher frequency, I don't see very much. Now I got it so I again get a single wave of a shorter wavelength. And if I get it going as slowly as possible, you see it matches here, but it doesn't match over there. So I'll get a long group. And that obviously isn't the one I want to measure. Let's go to a higher frequency. And I'll go to a still higher frequency here. Put it on the B channel. Go up to another higher frequency where it again stands still. There we go. Now I can show one going through the other, and I can show my group. I can go to a still higher frequency. And get a clean pattern. You see, I get all kinds of things depending on the relative sweep rate. Now I got another pattern. And I'll get a shorter group when I put them. Now they match in two places, and so I'll get still shorter groups. And so on. I can go up to very big differences in frequency and get even shorter groups. And that's all that the experiment involves, is measuring the wave and group velocity for various frequency differences between the two audio oscillators.
Experiments in Physics with Dr. Frank Oppenheimer is produced by the University of Colorado Department of Physics and Astrophysics in cooperation with University of Colorado Television. This is University of Colorado Television. Experiments in Physics with Dr. Frank Oppenheimer is produced by the University of Colorado Department of Physics and Astrophysics in cooperation with the University of Colorado Television. Today's experiment
This is the experiment.